Irodov problem number 1.124. A chain of mass m and length L rests on a rough surface table so that one of its ends hangs over the edge. The chain starts sliding off the table all by itself, provided the overhanging part equals eta of length of the chain length, so 1/3 of the chain length. What will be the total work performed by the friction forces acting on the chain by the moment it slides off the table completely? Okay, so let's say this is the table, okay, and let's say we have the chain that is resting on the table and part of the chain hangs from the table, okay. Okay, so the total length of the chain is L, and initially part of it hangs, which is eta L. So the part of it that is resting on the table is 1 minus eta L. Okay, right now this is just at equilibrium, but moment, like this is the edge case, it would start sliding off as soon as it is eta L. So we can say like this is the limiting case. So if this is at equilibrium, what is not given is what the coefficient of friction is. Okay, so just let's look at this state as of now. So what we can say is, if I draw the free body diagram of this part of the chain, so its mass will be total mass m divided by total length, so m by L, times 1 minus eta L. So LL gets cancelled, times G. Okay. The reaction from the surface of the table is N. There is a friction force F, and we can imagine that there is some tension in the string or in the chain, which is T. Okay, and this is exactly balanced out right now. Similarly, this part of the chain, we can look at the free body diagram. So this part will be m by L, mass times eta L times G. So LL gets cancelled, and this is supported by the same tension T. Okay. Now, if all of this is in equilibrium, we can write N equals m 1 minus eta G. So friction force is Kn or Kmg 1 minus eta. Okay. Similarly, tension and friction are balanced here, so tension must be equal to the friction force, and similarly here tension and the gravity force is balanced, so we can write m into eta G. So from there we can use these three. So friction force, which is Kmg 1 minus eta, is equal to the tension force, which is mg eta. So mg we can cancel out. K becomes eta divided by 1 minus eta. So eta is given as 1/3, 1 minus 1/3, so 2/3, so 1 by 2. Okay, so we got the coefficient of friction. Now let's look at the situation, what happens after some time t. Okay, so the initial position was here of the chain. Let's say it has slid off a little bit. So now the chain is hanging more, it is sliding off in the process of falling down. We will just look at some time t, after time t, what is the situation. Okay, So let's say this has slid by a distance x. Okay, so what is this distance then? This is 1 minus eta L minus x. And what is this distance then? This length is eta L plus x. Okay. Now let's just look at this part of the chain. So if I draw a free body diagram again, so this will be mass of this part of the chain times g. So what is the mass of this part of the chain is m by L into 1 minus eta L minus x times g. Okay. And there is some reaction N, there is this tension T, there is this friction force F, but now the difference from here is there is some acceleration that is happening in this direction. Okay. Similarly, if I look at the free body diagram of this part of the chain, we can write as m by L times this length of the chain times g, and that is tension on the chain in the upward direction, and this is falling by acceleration A. Okay. Now all I need to find out is what is this friction force. So the friction force will still be Kn, the coefficient of friction, times the normal reaction. And the normal reaction is still equal to the weight or force of gravity on this part of the chain. So we can simply write K m by L 1 minus eta L minus x times g. Okay. Now let's just substitute the value of, or let's just keep K just like that. Okay. Now work done by the friction force is, if we know the force and if we know the distance that it has traveled, so force of friction is on the left side, however the displacement is towards the right, so it has to be minus. Okay, so we can write f dx integral. Now what is the range of x? It's 0 to this length, so 0 to 1 minus eta L, because the friction forces will only be applicable up until the time the chain has completely slid off the table. So what is the displacement of the chain is from 0 to this length. Okay. All right. So let's do this integral. This should be pretty simple. So we can write minus 0 to 1 minus eta L. Let's just substitute this. So this becomes kmg by L, which is the constant part. And then in brackets, it is L minus eta L minus x dx. Kmg 1 L minus eta L minus x. Okay. Now integration of this is, if I take out the constant kmgl, it will be Lx minus eta Lx minus x square by 2, and the limits are 0 to 1 minus eta L. Okay. Now let's substitute the limits. So L times 1 minus eta L minus NL times 1 minus eta L minus 1 minus eta square L square by 2, and this will be all 0. Okay, and we can cancel. If we put down the values, then the work done by the friction force is equal to minus kmg L by 2 1 minus eta square, right? So k is half mg L by 2 and eta is 1/3. 1 minus 1/3 square. So minus mgl by 4, and this becomes 2/3 or 4/9. 4 gets cancelled. So this is minus mgl by 9. So that's the answer.